Welcome back, everyone. Today we are exploring a major structural shift in deep learning. Up until now, you have probably heard of convolution neural networks or CNNs as tools exclusively used for computer vision. Things like facial recognition or self driving cars scanning pixels. Today we are going to learn how to pivot that exact same technology to understand natural language. We will look at how neural network can treat a sequence of words just like an image grid, mapping out spatial patterns to find deeper meaning. Our roadmap covers three main steps. First, the foundational matrix math behind a convolution. Second, how we shrink data down using a process called pooling. And finally, how to write production code in Keras to build a network capable of detecting sarcasm in news headlines. Let's jump in. Let's start with the core intuition behind a convolution. Filtering for patterns. Imagine looking at a large grid of numbers, our input data n by n. To extract specific features, a CNN slides a smaller window called a filter or kernel f by f across that big grid. As the filter hovers over a section, it performs a basic arithmetic. It multiplies overlapping numbers together and adds up the total to create a new, smaller grid called a feature map. You can see the math highlighted on the slide. Multiplying our orange box by the filter grid shrinks that entire section down into a single number 5. Notice how the grid shrank from a 4 by 4 to 2 by 2. This brings us to our green box at the bottom, the dimension rule. Every time a filter slides across data without any modifications, the resulting output matrix will shrink according to the formula n minus f plus 1. Now that we know filters shrink data, we have to deal with two variables that alter this behavior. The first is padding and the second is strides. Look at top half of the slide. If we just slide a filter normally, the numbers in the center get touched multiple times, but the edge pixels are only sampled once. This means the model loses information along the borders. To fix this, we use zero padding. We wrap our input matrix in a border of artificial zeros. This gives the filter room to step outside the original data, ensuring the edges are fully analyzed and keeping our output size from shrinking. Next is strides, which is simply the step size of our sliding window. A stride of 1 means the filter moves 1 pixel or a word at a time. A stride of 2 means it skips a spot as shown in the orange diagram, drastically cutting the output size. When you combine them, you get the ultimate master formula at the bottom to calculate exactly how large your data grid will be after a convolution. Once our filter creates a feature map, we want to condense that data even further. This is called downsampling, and we do it using a pooling matrix. Pooling has a twin goal: keeping our computer's memory footprint light and creating a spatial invariance, which just means the network can recognize pattern even if it shifts slightly. There are four ways to pool data, as shown by the colored arrows. Max pooling is the absolute industry standard. It looks at a block and extracts only the single highest value, capturing the strongest signal. Average pooling calculates the mean of the block to smooth things out, while some pooling simply adds everything up. Pay special attention to global max pooling in the bottom right. Instead of looking at small local blocks, it scans the entire matrix globally and pulls out the absolute highest number, flattering our multidimensional data into a clean 1D line that is ideal for text sequence. Here is the critical pivot of today's lecture. How do we jump from a 2D images to 1D text? In an image, pixels have a two-dimensional relationship. They connect up, down, left and right. But text flows in a single direction over time, creating a 1D sequential relationship. Therefore, we use a 1D convolution, conv1D, that slides vertically down our words like a scanner. Let's walk through the pipeline on the slide. In step 1, our sentence is broken into individual words which are called tokens. In step 2, those tokens are converted into dense 300-dimensional word-to-vec vectors, creating our text matrix. In step 3, our conv1D filter slide vertically over blocks of words, acting exactly like a moving n-gram window to catch multi-word context. Step 4 applies global max pooling to grab the most critical semantic features across the whole sentence. And step 5 passes that line into a dense layer to output our final classification, sarcastic or not sarcastic. In this system, we have to look at how we format our data pipeline in Python. Our neural network expects incoming data matrices to have identical shapes, but news headlines are naturally different lengths. To solve this, we force every single headline into a rigid tensor structure. As seen in the code block, we set a max length of 10 words and a vector size of 300 because of our word-to-vec embeddings. We then run a loop. If a headline has a word, we append its 300 value vector. But notice the final conditional check, algorithmic padding. If a headline is short, say only just 4 words long, we automatically fill the remaining 6 slots with an empty padding, vector of zeros. This acts exactly like the edge padding we saw earlier, guaranteeing every headline enters the network as a flawless, uniform 10 times 300 grid. Let's talk that structured pipeline and feed it into our Keras model architecture. In layer 1, we add our conv1D. We specify filters 8, meaning the network will look for 8 distinct semantic patterns simultaneously. We set kernel size here 3, which tells the model to slide down the text 3 words at a time, meaning it is explicitly reading phrases as a 3 grams. In layer 2, we applied global max pooling 1G method. This scans those 3 gram features, outputs and isolates only the absolute strongest activation signals, throwing away the rest to protect against overfitting. In layer 3, we pass those pooled features into a fully connected dense layer with 10 nodes to mix our signals, accompanied by dropout layer set to 35% to force the network to generalize its learning. Finally, layer 4 is our binary classifier, a single node using a sigmoid activation function. This squeezes our complex math down into a single decimal number between 0 and 1, representing the probability of whether a headline is a sarcastic or sincere. To wrap up our build, we compile and train the model. Because this is binary classification task, we use binary cross entropy as our loss metric and pair it with the Adam optimizer to smoothly adjust our weights across 10 full passes or epochs of the training data. Take a look at the scale of this network on the left. It has 7,359 trainable parameters. That means during training, the network is computing loss gradients and fine-tuning over 7,000 unique internal weights to separate sarcasm from literal statements. The payoff is on the right, a 76.1% accuracy rate on completely unseen testing data. The big takeaway here is the validation. By structuring language as a sequential 1D matrix, we prove that convolution neural networks can capture structural semantic nuances incredibly well, a linguistic capability traditionally thought to belong only to complex recurrent neural networks.